Okay, this video is about section 10.4, which is on absolute and conditional convergence. And the question here at the top of the notes is hopefully one that you've maybe been asking yourself. So the last section, if you remember, was 10.3, and it was about dealing with series with only positive terms. And so we did integral test, limit comparison test, and comparison test. So hopefully the question you're asking is, what do I do with series that have negative terms? And we already have a couple of small sort of tests that we can do with very specific types. Geometric series can have negative terms, but it has to have that very special form. We can do some stuff with the negative terms if they're telescoping, right, and that they're going to cancel each other. But in general, right now, we don't have any series tests for things that might look like the sum of -1 to the n of some, like, some fraction n squared over n cubed plus 1. We don't have something necessarily for that. And we also don't have something for things of the form maybe that looks like this, like sine of n over n. So this is something we wouldn't know much about how to deal with that, because those terms are both positive and negative, right? So I think in the last section we did some that had absolute values around it, and those would be good to go in the previous section because those are positive. But if you remove these absolute values, then these terms could be positive and negative. And the question is, how do we deal with those kinds of things? Because right now, we really only have tests for things that are positive terms besides those few small cases. So we'll start out with a few definitions. First of all, a series is absolutely convergent if the series of absolute values, so the sum of the absolute values of the ANs is convergent. So that's a term that we'll talk about, is absolutely convergent. And this first theorem here is one that we'll use quite often. If a series is absolutely convergent, then it is convergent. So if you can show that the positive version of the series is convergent, then we know that the series without the positive terms is convergent. So this is great, because if we can take the absolute value and show that that series is convergent, then that means we can go back and use our series test for positive terms. That's great. Then we know that the series without the absolute value signs around it, with the negatives or whatever, is convergent. So that's a really nice theorem to be able to use to go back to use the convergence test that we learned in section 10.3. So that's absolutely convergent. The other idea here is, if it's not absolutely convergent, what would we call it? And that term is conditionally convergent. And we say something is conditionally convergent if it converges, if that series, the sum of the ANs, converges. But if we take the absolute value, that series diverges. And so we're going to look at a few different examples here to get used to this terminology and think about how to use this particular theorem right here as sort of a series test of a sort. So let's look at this. It says to verify the convergence of this series, 1 over 1 squared minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared. So hopefully you can recognize the pattern there. So if we start this sum at n equals 1 and we go to infinity, looks like it's n squared in the bottom. And on top, it's clear that the signs are alternating. And the question is it alternating -1 to the n or -1 to the n plus 1? And if we're starting at n equals 1, that would be positive, negative, positive, negative. So if we raise it to the n, we would get a negative right when we plugged in 1, and that would be the opposite of what we want. So I'm going to do to the n plus 1. So there's our series. That's S. And if we take the absolute value of our terms on the n side, the absolute value of -1 to the n plus 1 over n squared, we should see pretty easily that that's just equal to 1 over n squared, because the negatives would go away. And since we know the series 1 over n squared converges by the p series, then we know that the series S also converges. And that's by this theorem, right? Because the series is absolutely convergent, the absolute value converges, and thus, therefore, the actual series converges. Or you can even say, then S, you could say, is absolutely convergent, because we know the positive parts converge. So if the positive parts converge, then we know that the negatives must also converge. So that's our first example of how to use that theorem. If you can take the absolute value, show that it converges, great, we're done, we don't have to do anything else. And that's awesome and that's easy. We can go back to all the things that we did before. But what about a series that is maybe not absolutely convergent? How do we go about dealing with a series like that? So that leads us to our next example. So let's look at this example. We have the sum, -1 to the n, say plus 1 over n, and again we'll start at n equals 1 to infinity. So if we look at this series, we get, looking at the absolute value, -1 to the n plus 1 over n, we'll get 1 over n. But we know that that series, the sum of 1 over n, diverges by the p-series. But we're going to show soon, in the next couple of slides, that this series, -1 to the n plus 1 over n, will converge. So this is a -1 to the n plus 1 over n is a conditionally convergent series. And this series is known as the alternating harmonic series. So remember we talked about the harmonic series in the last section. This is the harmonic series, the 1 over n. Now this is the alternating one, and the 1 over n one diverges, but the alternating series converges. And the question is, how do we show that, right? How do we show? I said we will show. The question is, how do we actually show that this series is convergent, right? The one with the negatives in it. How do we do that? And that's what we introduce here in this section. We get one new test. So we've learned 3 tests in that last section. This one we really kind of get the theorem that we just saw. If it's absolutely convergent, then it's convergent. And we get this kind of big test. So I guess we kind of get 2 in this section, but this is the big test. So let's take a look at it. Okay, this is the Leibniz test for alternating series tests, or alternating series, and we abbreviated the AST. So if you want to use that abbreviation, that's completely fine. And here's how it looks. So we start with an alternating series. So it's got to be a series that has both positive and negative terms. So it's like -1, let's say to the n minus 1, b sub n is b1 minus b2 plus b3, so on. If that satisfies 2 things, first of all, bn plus 1 is less than bn for all n. And secondly, if we take the limit of the bn's, ignoring the negatives, if that goes to 0, if those 2 things are true, then the series is convergent. We also know that the sum s is less than or equal to a1. I'm not sure what a1 is. Maybe that's supposed to be b1. And s of 2n is less than s of 2n plus 1 for all n. And so I want us to kind of look at a visual of this so we can kind of get a sense of what this is and where it's coming from. But the first thing to note is that another way to think about number 1, if bn plus 1 is always less than or equal to bn, people have an idea of what that means? So in other words, bn is decreasing. So it's getting smaller. So the first thing is to check that it's decreasing. The second is that that limit as n goes to infinity of those bn's goes to 0. So those are the 2 conditions that you check. And instead of proving this theorem, I just kind of wanted to give you a visualization of how this series is sort of working. So let's say we're down here and we have this sort of number line representation. We start at 0. And maybe the very first thing that happens is we take our b1, so this is b1, and it's a positive term. We'll assume it's positive to start with. And we get this, right? So this is b1. And so that gives us a sum, right? Sum 1. The first partial sum is S1. So we take b1, right? We add it to 0 because we start with nothing and we get out here. Now remember, the next term is subtracted. So we're actually going to start here and move backwards by sum b2. But remember, b2 has to be less than b1 by condition 1. So we know that this is smaller than that. So we know that this line will not go past 0. And then when we add those two things together, right, we'll get our second sum, S2. And then again, we'll move in the forward direction because the next term has to be positive. It's an alternating series. Here's B3, and that would give us the third sum. So keep remembering that this series has to be decreasing, so I can't take this line past this dotted line here, the vertical dotted line. So maybe this is B4. And this keeps going, right? And we keep doing this. And remember, the other thing is that this limit is getting close to 0. So these lines are also getting infinitely small, right? As we get down here, they're going to be shorter and shorter and shorter. And hopefully at some point, we're going to come to an S, right? The sum of this series. And that's the idea of the alternating series test. Because the first condition is that these lines are going to be getting smaller, so they're never going to go past where you started. So you're always going to get here, subtract back, add, subtract back, add, subtract. So you're never going to go too far past your very first sum. You're going to come back, you're going to come back, you're going to come back and forth, back and forth, back and forth, and eventually end at S. That's what the first condition says. The second condition guarantees that these lines get small enough so that we actually do approach an S. Because if they were going toward a certain number, then maybe the lines would kept getting bigger and they wouldn't maybe level out to one particular sum. So that's the idea. And then the other big thing, if you'll notice here, the sum has to be smaller than S1 because that's your very first thing that you add is to come out to S1. So your sum has to go somewhere below that because you're going to come back and up, but you're never going to come all the way back up to S1 because of the decreasing feature of this. Unless they're all equal, and you may end up at S. And then the other big thing about S is that it's always between 2n and 2n plus 1. So in other words, if you take any two numbers, right, S2 and S3, your sum is always going to be between those two partial sums because you're going to come up and then you're going to come back down. So that's what these little two pieces are kind of also represented in this nice picture here that I enjoy for this, thinking about how the series test works, is that you add, you subtract, you add, you subtract, but the key thing is you're never adding or subtracting more than what you originally had, and eventually the things you add or subtract are going to get really, really small. So that's the alternating series test. That's what we're going to use to take pretty much there's one more section in the series test, and that one has some opportunities for you to do both positive and negative terms. But this is what we'll use for now. This will be our kind of go-to series test for things that have negative terms in them. So let's try some examples of this and see what we can. So it wants us to determine if the series converges absolutely, conditionally, or not at all. So this is our first one, the sum n equals 1 to infinity negative 1 to the n plus 1 over n. This is our alternating harmonic series that we talked about on the previous page. Now we're actually going to show that it does, in fact, conditionally converges. So first we notice that, number one, the first condition to check is that 1 over n plus 1 is always certainly less than or equal to 1 over n. So that's a check for condition 1. Condition 2, the limit as n goes to infinity of 1 over n, because remember we ignore the negatives, is equal to 0. So that's a check. And we know, so that means by the alternating series test, that this series, negative 1 to the n plus 1 over n, converges. But since we know that this series, 1 over n, diverges, we say that this series, negative 1 to the n plus 1 over n, is conditionally convergent. So it's a conditionally convergent series because of the fact that we know that the regular harmonic series diverges, and this series, using the two condition check of the alternating series test, is it decreasing? Yes, it is. And is the limit going to 0? Yes, it is. So as soon as you can show that those two things happen, we're good to go. If either one of those things fails, if the limit is not 0, then that actually goes back to the test for divergence. But if this thing is increasing and you get that, then you actually don't get much information. You have to try something else. So it's important to make sure you checked both conditions, because if you don't check both, then we're not conducting the full alternating series test. So now if we look at this guy here, we have 1.1 to the negative n, and that's times cosine n pi. And so when you first look at that, it doesn't look alternating. Maybe, maybe not. But please recognize, right, that the cosine terms could have negative values. And in fact, these are cosine of n pi. So if we think about that, cosine of 0 pi is going to be 1. Cosine of 1 pi is going to be negative 1. Then we're going to get 1, negative 1, 1, right, if we keep going around the unit circle. So I would even take the opportunity here to convert this to make it look more like an alternating series. So this is really, let's see, these are negative 1s, and it starts out positive, so I think that would be raised to the n, right? Because the 0 gets a positive 1, 1 gets a negative 1, 2 gets a positive, 3 gets a negative. So I think we want to put that with whatever the n is. So there's our term, and we can even rewrite this if we want. Again, I don't know if it's clear, but we could even rewrite this further as negative 1 over 1.1 raised to the n, because this is to the negative n, so this part raised to the negative n means that's going to go to the denominator, and then we can put everything raised to the n. And now, hopefully you recognize that as a geometric series. And the geometric series, this is an r is equal to negative 1 over 1.1, which is really 10 over 11, negative, which is less than 1 if you take the absolute value. So we'll do that. The absolute value of all that stuff is less than 1, and so converges absolutely, because the positive terms converge, and therefore the negatives also do by the geometric series. So in this case, we didn't even need to use the alternating series test. And in fact, the alternating series test actually might be tricky here. You'd have to show, you have to rearrange it, and then you'd want to get that rearrangement. You'd have to show that it's decreasing. So as we get a bigger and bigger power, why is this thing getting smaller? And then you'd also have to guarantee to me that the limit as n approaches infinity of this thing, negative 1 over 1.1 to the n, or I guess 1 over 1.1 to the n, because we ignore the negative, would also go to 0. So, there are a couple of options there, but I think this one is a little bit quicker once you realize that all it is a geometric series, and that takes some of the time and work away from you all. So hopefully those examples help you see a little bit about how the alternating series test works. The main thing is that you just need to check these two conditions. And remember, if this isn't obvious in your decreasing, you can always show decreasing by taking the second derivative to show you can take that to equal an, and then you can show that f prime is always less than 0. So that's the other thing to remember, is if you can show your derivative of your function is always negative, then you will have you'll have shown that the terms are decreasing. So that's another option for the alternating series test. There's a second video for this section, which is about how to actually estimate an alternating series. And so we'll post that one as well. So if you want to watch that one next, that would be great.